Okay, so we continue. So in the case of Bose-Einstein and Fermi-Dirac statistics, um, we can obviously substitute this expression, right? G of B, this was equation number 5 and 6, I suppose, which we have written. So these expressions can be substituted into equation number 4. So in either case, we know that the value of G for admissible values of NE is 1. So therefore, I can write in the case of by Bose-Einstein FT statistics, expression for Q and Vt as equal to sum over Ne, the distribution Ne, e raised to minus beta sum over E Ne E. Okay. Right. And of course the difference is in the difference between Bose-Einstein and Fermi-Dirac is with respect to its Ne values, admissible Ne values, right? For Bose-Einstein we can have any value of Ne, whereas in Fermi-Dirac you can have either 0 or 1. So that's the only difference which happens to this expression. So this is valid. This expression is valid for both Bose-Einstein and Fermi-Dirac. So how will we extend that to the grand canonical ensemble? The same thing for Bose-Einstein and Fermi-Dirac situations. Theta of ZVT is equal to sum over n is equal to 0 to infinity z raised to n, right? Z raised to n sum over distribution Ne e raised to minus beta sum over Ne E, right? And this Z raised to n, right? So this we have written in the beginning of our derivation in one of the previous videos. I think it was equation 3, I suppose, that it was sum over Ne is equal to capital N. So I can substitute that idea over to here and take it inside the inside this derivation, inside this term. So if I take that over there, I can write this as equal to sum over n is equal to 0 to infinity sum over Ne product over E Z e raised to minus beta E raised to Ne. Right? Why product? Because we have the summation of an exponential term. So which can be expressed in terms as the product of its x values. So that is how we have done it. And in order to accommodate x z also, we have taken this whole term and raised to the power Ne. So we got this expression. Now we are in a convenient situation where we have two back-to-back or two simultaneous summations concerning the same set of particles. So these two together I can express as the summation over the number of states or all possible values of states. So which can be expressed in terms of Ne values. So sum over Ne or I can actually it is more correct to write it as n0, n1, n2, etc. In any way, let me put that also. So sum over Ne product over E, Z e raised to minus beta E raised to N. Okay, and now, which means that which can be expressed in terms of the Ne values. So what is the values of Ne possible? Ne stands for the number of particles in a particular energy level, right? It is N0 means the number of particles in the energy level 0. N1 means number of particles in energy level 1, etc. etc. So what are the possible values of N0? N0 can be any number, like 0, 1, 2, anything, right? If provided, if it is a Bose-Einstein or the Fermi-Dirac situation. For the Fermi-Dirac and the Bose-Einstein or the Maxwell-Boltzmann. For the Fermi-Dirac, I can have only two values for N0, either 0 or 1. Similarly, for N1 also I can have 0, 1, 2, etc. for the Bose-Einstein situation. So that is how we have to accommodate that. Since this in this expression we are expressing doing the summation in terms of the number of states, it physically means that I have to take the product separately for N0, N1, N2, etc., where I will substitute the values of N0, N1, etc. So the above expression can be written as equal to sum over N0. I took only the case of the 0th level of energy, N0, Z e raised to minus beta E0 raised to N0 into sum over N1 Z e raised to minus beta E1 raised to N1 into etc. So you will have sum over N2 term, you will have sum over N3 term, and so on and so forth. Okay. This is a product of all those things. Now this can be expressed as so what are the possible values of Ne? 0, 1, 2, which means as I have written here, N0 can have 0, 1, 2, N1 can have 0, 1, 2, etc. So that is why the summation over here comes. So here in summation, if it is a Bose-Einstein situation, I have to do the summation by first substituting raised to 0, raised to 1, raised to 2, raised to 3, and all those things into for the particles in the first energy state, which is N1, and again 0, 1, 2, 3, and all those things. That is for the Bose-Einstein. But for the Fermi-Dirac, the situation is you have to take, and the job is more easier, where you have to take either N0 is equal to 0 or N0 is equal to 1. Okay, so which means that I can simplify that and write it as theta ZVT is equal to product over E. I can now express this in terms of the expansion for 1 minus x. I will write it down. So if I write out that expression, use that connection, I can express the theta as 1 minus Z e raised to minus beta E. So the expression which I was talking to you was, I don't know if you know the expansion for 1 by 1 minus x can be expanded as 1 plus x squared plus etc. provided for x lying between minus 1 to plus 1. So For this expression, I have used the expansion of this one. So each of this term over here, right? Each of this term over here can be expressed in terms of the 1 minus x. So it will be a products of different 1 minus x terms. Right. So this is for the so here this equation will have a condition, right? Because x has to lie between -1 to +1, which means that in the Bose-Einstein case, I have the limitation that z e raised to minus beta e should be less than 1. Okay. So that is one condition which this equation has to satisfy. So z e raised to minus beta. So this condition you have to remember. We will need that at some point of time in the next video itself. So that is it for the. So what will be the corresponding equation for the Fermi-Dirac? There, in that case, here we will have only two terms, n0 term and n1 term, and within that term, I can have for the n0 and n1 or n2 etc. whatever be the energy level it be, there can be only two particles. So each of these things in the square bracket will have only two terms. It can be either with 0, it can be either 1 or it can be z e raised to minus beta e. So therefore I can write this as product over e 1 plus z e raised to minus beta. So this product over E will take care of any level of energy possible. And so those are the expressions. And if we now write down corresponding Q potential, we know that Q is equal to PV by KT. And we know the connection for it with the partition function as ln theta ln of theta is at Vt. So if I apply the ln in these expressions, I can write down the common expression as minus or plus sum over E ln 1 minus or plus z e raised to minus beta e. So that is a general expression for partition function. Okay. So this is a simplified form. You can always try yourself taking the ln in this case and ln in this case, and you will always land up in this expression. Okay. So now we have to discuss something on the mean occupation number, which we will do and we have to develop a plot based on the variation of mean occupation number, which we will do it in the next video.